Okay, so having looked at some sampling objects in Max, we'll look at some synthesis ones, some very basic ones, so that we can get sound using oscillators. So this very simple patch here is slightly different from the one that I've given you to copy out. That's because this multiplication object here does the same thing as the gain control here. I'll come back to that in just a minute. So what do we have? We have the normal easy DAC out, the gain control, and a cycle object, which produces a sine wave. So this is what a sine wave looks like, or broadly. It's a little bit pixelated, but it gives this very smooth wave that goes. Well, you can see the numbers here. Actually, we have a central point of 0, and sort of extremes of 1 and -1. The curve goes from 0 to 1, and then back through 0 to -1, and then back to 0 to our kind of rest point. And you can see this is emulating the movement over time of your speaker cone, pushing outwards at this point, and then coming back through its rest point, back to a kind of pulled back, and then back to a rest point. And if you do that quickly enough, then it yields a sound. So we will make it read through. So cycles through this shape repeatedly. And we can specify the number of times it cycles through this shape per second by sending this a number from this float number box. So if I turn up the volume a little bit, we don't hear anything because we've got this shape happening at 0 Hertz, so 0 times a second. We wouldn't hear anything until we reached about 20 Hertz. I need to crank up the frequency more than that if I want to hear anything on my speakers. Still not hearing anything. Oh, there we go. I can hear something now. So we have this very characteristic, smooth tone, which is kind of archetypal sine wave. So that's fine, and we'll look at a few other oscillators in a minute. I'm going to come back to this gain control here and compare it with what I asked you to do with this multiplication object. So you'll see that if I lock the patch and get rid of this gain control and make a multiplication object in its place with the same value as I've asked you to put in, you'll hear that we hear the timbre again. And if I send a number to this multiplication object, then by changing that number up and down, then I am doing exactly what I would be doing with a gain control. I'm amplifying and attenuating that signal. So why is it that that multiplication object is doing that? And why would you want to use it in the first place? Well, we'll come back to that in a minute because there's an example I want to show you where we will use it. But I've got a kind of example patch here which will hopefully make this a little bit clearer. So I mentioned before that our cycle object is producing a sine wave that goes between 0 to 1 to -1 and back to 0. So our extremes of available loudness on a computer are between these values of 1 and -1. Anything in between is a value between those numbers. And each one is a sample. So when we are amplifying or attenuating a signal, we are multiplying each one of those values by a number. And if we multiply it by 0, so this is our original signal that's being generated by the cycle object. This is our output. And when I'm amplifying by 0, then each one of these samples is being multiplied by 0. So 0 is being multiplied by 0, which gives us 0. 0.01, for example, is being multiplied by 0, which gives us 0. 0.02 is multiplied by 0, which gives us 0, and so on. If I multiply everything by 1, then we can imagine that we will get the same values out that we put in. So 0 multiplied by 1 is 0, 0.01 multiplied by 1 is 0.01, 0.02 multiplied by 1 is 0.02, and so on. When we get to 1 multiplied by 1 is 1, down to minus 1 multiplied by 1 is minus 1, and back to 0. So each one of these samples, which you can see effectively represented in this graphic by the kind of pixels, each one of those is being multiplied by a number, which I'm specifying here. And so anything between 1 and 0, so we could give it 0.5, means that obviously we attenuate this overall signal by a half, and that gives us a quieter signal. We could also multiply by a negative value, and notice that when we do that, so I'm going back to 0 and then I'm inverting this. So what happens? Well, we're inverting the phase. So if I were to play these signals alongside each other, we would essentially cancel out the signal altogether. So that's the reason why we're using a multiplication object, and it works with any signal. So let's put this on 0 again. If I make a pseudo-random signal, which this is much more like what you would get with an input from, say, a sound file, much more complex. But the same thing applies, so if I multiply this by 0, every sample that you see here is being multiplied by 0 and we get 0. If I multiply everything by 1, then we get the original signal, but we can attenuate that to 0, and then beyond 0 we end up inverting the signal. Going back to the sine wave, what happens if we multiply above 1? Well, at that point, because the system can only accommodate a certain number of values between -1 and 1, if we go above those, then we end up with clipping. So this is what clips the signal, and this is what you get in Pro Tools or any other DAW, where you crank up the signal too much, then because the system can only accommodate so many values, then it will clip. You'll get digital clipping. So if you were to have your input signal going between 1 and -1, which this cycle object does, then you amplify it by more than 1, then you're going to get that clipping. A pseudo-random signal, if I had a signal like this where the original signal is not going anywhere near 1 or -1, then of course I can amplify that by more. But at some point, in this case, if I multiply it by more than about 1.7, then it starts to clip just as it would with anything else. And you can see this kind of table topping that happens at the extremes of our bandwidth. Okay, so that's just to point out why, what multiplication is doing. I'm sorry if I've laboured the point, but I felt it was worth explaining properly. So, where can we use that? Well, here you'll see that we've got both. So I'm going to make this a little bit bigger so it's easier to see. We have both an overall gain control here, and we also have a multiplication object just above it. So why do we have both? Well, one is, just as I said before, really, an overall gain, whereas this one is helping us to handle the velocity information from when we hit a key. So if I were to connect this to my launch key, which I will do, so I'll do a note in from channel 1, and I'll connect the outlet from the note in object to the left-hand inlet of kslider and the right-hand outlet of note in to the right-hand inlet of kslider. So this one accepts note information, this one accepts velocity information. You'll see velocity value received. So I hit a key. Let's turn this on and up. So now we have what we expect, which is that the keys yield a note. And you'll notice that if I hit the key harder and softer, we hear the note being either louder or quieter. And that's because if I connect a float to the output of the velocity output on the kslider, which is just throughputting this data from note in object. When I hit the key, you'll see a number between 0 and 127. So if it's moderately hard, then I get 86. If I hit the key harder, then we get something closer to 127, and 127 if I hit it really hard. But you might remember from the previous patch that our numbers were only between 0 and 1 for multiplication. Again, if we were to multiply by too much, then we would get clipping. So we need to scale that range from between 0 and 127 to between 0 and 1, which is what we're using this for. And since our range is only from 127, 0 to 127, then if we divide any of those numbers by 127, then we can only get a value between 0 and 1. So if I make a float object, we'll see that happening. So if I hit the key hard, and we get 127 out of note in and then subsequently out of the kslider, we divide that number by 127 and we get a value of 1, which means we're amplifying cycle as whatever's coming out of cycle by as much as we can, and we get full bandwidth. So the sound is as loud as it could be. Notice that when I release the key, we get a value of 0. Remember that note offs are the note number and a velocity of 0. So when they come out, everything is divided by 127, so we get 0, and the note turns off. If I hit the key moderately hard, so we get 67 out of here, then you divide that by 127, and we get a value of 0.5-ish. So about half as loud as it can be, and you'll notice that the volume here is attenuated. Because this is a logarithmic scale here, we're not seeing it. It doesn't look as though it's half, but in fact it is half the energy. And then if we go even quieter, there we go. Oh, that's very quiet. So that's a velocity of 3 divided by 127 gives us 0.024, and this one is noticeably quieter. So hopefully that makes sense of this business here, and you'll come across this multiplication object quite a bit in relation to amplitude. So just to point out this other object here, which is doing something with the note information that's coming out of the left-hand outlets of both note in and then kslider. So what is it doing? Well, M to F stands for MIDI to frequency, and I think I ask you to look at the help window. So I click on Alt and the object, and it comes up with this help file, and it tells us convert a MIDI note number to a frequency. So you remember that each key of the keyboard is allocated a number, and so if I hit this one, which is middle C, we get the note number 60. But the thing is that the cycle object can only handle frequencies, which I don't think I made very clear earlier on. But the default that I put in here was 440, so it was 440 Hertz, but it will only stay at 440 Hertz for as long as I'm not sending anything new into its left-hand inlet. When I do, then it will play the frequency that's input. So when I hit the key C on here, I get the note number 60, and M2F then spits out the frequency of 261.6258 Hertz. If I hit the note A up here, then notice we have a key number of 69, but that has been converted to a frequency of 440. So we're getting the appropriate frequency for the object. And incidentally, if you really wanted to know, there is some maths going on under the hood, which if you were to do it yourself would look something like this. In fact, it would look like that. Thank goodness you don't need to do that. But that is the equation or the expression that's required in order to perform that calculation of converting a MIDI note number to a frequency. Again, you don't need to do that because this object does it for you. So, press a key on the keyboard. The M2F object converts that from a MIDI note number, as we see up here. Let's get rid of this comment, to a frequency, as you will see here. So 60 to 261.62558 for the note middle C. An octave below that we get the note number of 48, but the frequency of 130.81279, which is half of 261.62558, and so half the frequency gives you an octave lower. So that's how this patch works. And so it reliably converts both MIDI note numbers and MIDI velocities to data that the MSP objects can use in order to make a sound of middle C at a velocity or a loudness equivalent to the violence with which we hit the key. So what else can we do with this? Well, we might want to try different timbres. So at the moment we've only got a cycle object, so we can only get our sine wave, which is all very well but not very interesting. So we'll introduce another oscillator, which is a sawtooth wave. And I could put an argument of 440 in there, but I'm not going to bother because I don't need one. In fact, I could get rid of that 440 Hertz in the cycle object as well. Now, saw works in very much the same way as cycle. It's got a wave table in it, but this time it's in the shape of a sawtooth. So if you follow my cursor, again, that goes between -1 and 1. So it would start at 0, jump to 1, ramp to -1, and then come up to 0 again, and then repeat the process again. So you get this sawtooth wave. Other than that, it does exactly the same thing. So connect the MIDI to frequency object to the sawtooth wave, and we get a sawtooth wave of whatever frequency we've specified using the keyboard. Now I could just connect that directly to this multiplication object again. If I did that, we would get both timbres playing at the same time. But because the sawtooth wave is more strident than the cycle wave, then it's going to be heard in preference to it. So we might want to choose to hear either or those two timbres. I just need a bit more room, so I'm going to pull this down. And so we'll use an object which allows us to choose between them, and that is the selector object. So what I need to do with the selector object is very much like a gate object. You have a series of gates that you can either open or close to allow signal through. So if I say I want 2 gates, or 2 means of selection between cycle and sawtooth, and I put in an argument of 2, and it gives me 2 inputs. And you'll see that if I hover over here, we get a comment that says, or a hint that says input 1, which is currently closed, or input 2, which is currently closed. And so I will connect these two to there. And then our output to the multiplication object. So having done that, what we need then is a means of choosing which of these 2 gates is going to be opened or closed, and we'll do that by means of a number box. So here, if I hover over here, it says or an integer or a signal, well, we're using an integer, turns the input off or routes to output. And just as when we were using a gate object, the number 0, or in the case of a toggle, the off mode would send a 0, and that means that nothing will be open. And just as with the toggle connected to a gate, if I turned that on, the number 1 would be sent, and that would open the first outlet. So here again we can send a 1, and that will open the first inlet of this selector object and provide us with a sine wave. Let's lock the patch. And then if I were to choose the second one, then we get the sawtooth. So we can choose between one or the other. neither if we give it a 0. So if you understand the principle of that, then you can add as many different oscillators and means of choosing between them as you might wish, obviously based on the number of oscillators that are available. So I'm going to add 4 inlets to selector, or 4 oscillators, and they are going to be rect, which is going to give it 0.5. Don't worry about the 0.5 for the moment. I'll come back to that in a minute. And a triangle wave, also 0.5. And once again, connect those to M2F. And here again we can hear any one of those. Okay, so we heard a square wave coming from the rect object, and we heard a triangle wave coming from the tri object. So yeah, just coming back very briefly to this 0.5 business. Basically it represents in both cases, the rect and the tri, what's called the duty cycle. And in the case of the square wave, or the rectangle object, but I could change that. So if I increase my numbers from 0.5 upwards, then we see that the relationship of the one portion of the cycle, or the cycle of the portion that is at value of 1, is increased and longer than the portion that's in -1. And so that would change the timbre. And I could change it the other way, so that we have a shorter period in a value of 1 and a longer period in a value of -1. This generates what's called a pulse train, and that has a particular characteristic. So we could actually change this kind of dynamically and have it changing sort of as the sound plays, and in doing so you'd get a kind of evolving timbre, which could be quite interesting. Similarly, for our triangle wave, this represents where the point is in that cycle. So it's going from -1 at the beginning to -1 at the end, through 1 at some point in the cycle. And if we change the duty cycle, then we can change the point along the horizontal axis where that apex is reached. And of course, as we move towards kind of more extreme ends of the table, then we get something more or less akin to a sawtooth wave. So again, that could also be changed dynamically during the course of a sound, and we'll get changes in timbre. So we can try that. If I were to, connect this up. Getting any sound, we'll choose the square wave. So this is a square wave at a duty cycle of 0.5. You'll hear that changes as we move through, or change, where the change from 1 to -1 occurs. Same again with the triangle wave. You get that sort of phasey character as we change where the point of the triangle is in that cycle. Most of the time, as I say, if you only want a square wave, then you would keep that at 0.5, or a triangle, you would keep that at 0.5. Finally, we could find a better way of describing which of the oscillators we're choosing from the selector object. And so I'll quickly introduce another object for you for that, and that will be the U-menu object. So as usual, I've got into the habit of writing those out into an object without actually bothering to find them in the list up here, but you should find it in interface, and here it is. So U-menu is a pop-up menu. so we'll be using that one. So in this case, what I need to do is to connect the left-hand outlet of that into the selector object. And it's not got anything in there at the moment, so there are no drop-down items. So we need to populate that with using the menu items in the inspector window. So click on Edit, and we can have we basically add items separated by commas. So if I put in off comma, then the first oscillator is a sine wave oscillator, and then the next one is a sawtooth oscillator. Next one is a square, because we're going to leave it as a square, and finally a triangle. So I put those in there, press OK, and they appear in this list. So when I lock the patch, then we get off, sine, saw, square, and triangle. And when I choose them, we get the appropriate sound. And that's because what the left-hand outlet is spitting out is numbers. So if I choose off, I get a 0. If I choose saw, I get 2, which of course is our second inlet here. Square gives me 3, which is our third inlet, and so on. So you have a way of choosing between those oscillators now. So we have a basic synth, a way of changing the amplitude both by an overall gain and by means of velocity, how hard we hit the key. We have a way of choosing between different oscillators using an intuitive menu. And we also figured out a few issues to do with the duty cycle and how you can modify a timbre even within these oscillators.